Now we move to talk about Spiro and Espadon, essentially. So the first one will be Claire Moutou, who will talk about Amakihi Community Survey, White Spectra.
So I'm presenting with colleagues here the proposition for the Amakihi Community Survey using Espadon Spiro in the command. And Amakihi, well, for those that don't know me, there may be two people in the room that don't know that I like birds, and it's a little Hawaiian birds. Okay, I had to say that. So it's the it's the community survey that would really use the Winao opportunity. We'll have an instrument that will be unique in the world, and so basically the big question of having a tilted spectropolarimeter is largely solved, as you saw yesterday in the talk. And this survey, especially, but in particular the exoplanet part, will really highlight also the usefulness of having optical that probes mostly atoms and infrared that probes mostly molecules. And it's something that just basically cannot be done with any other facility in the world at once. Of course, you can always stitch data together at the end, but that's not the case here. We'll get it at once. The stability of Espadon is not 1 meter per second. We may improve it. That's a goal. So, and also the idea would be to obtain observation of both modes. The true interest of having either optical or infrared for some targets is less. If you observe TRAPPIST-1, it's not that exciting to get Espadon, but you may get interesting ancillary data such as H-alpha, things like that. So, of course, it's a single source survey, so you're not pointing, that's not IFU. Typically, most targets will be bright objects, and for most programs, we're thinking time domain, so sequences through the life. There's exoplanet science, both transit eclipse on one side and masses, either guided or not guided. We'll come to that. So PRV, stellar science, and galactic archaeology with chemistry. And also, it's important to keep in mind that it's complementary to space missions, ongoing or coming. So GWST, ongoing, of course. Gaia, follow-up of astrometry. Plateau, Ariel, HWO, ELT, but it's not space, but no. You see the idea. The first work package, the one, it's in the same vein as what we had for the SLS spice planets. It's the architecture of exoplanet systems. So one key thing is that when the ELTs arrive, or the ELT maybe without an S to start with, you want to know how many systems there are very close to us, which one can be directly imaged. That's important. We want to understand the architecture of these systems, the occurrence of planets in the habitable zones. We're still discovering. You saw the papers that Claire mentioned and others, Merwan mentioned. Understand the planetary mass function, the interaction with the host stars, of course. Find the closest habitable. So there are two parts. There's part of statistics. There's also parts of stamp collecting. It's very pejorative, but you want to know which ones are the nearest ones that could be further studies with other techniques. Also, the link between the stellar properties and the planet properties, and where can we find life nearby. So basically, it's follow-up of what has been done already successfully, RV monitoring, characterization of the host stars with the rotations. We're establishing rotations, as I mentioned, with the DTEM, with spectropolarimetry also. Focus on the samples of about 50 to 100 stars with regular monitoring. We don't like the moon with bright, dark time, okay? Secret, we one day would like to get some dark time, just saying. Okay? Just saying, okay? I said it. We also have long periods, so there are longer periods also in PRV world. So we want to follow up some objects that are unknown. Most of this is done in circular polarization because it's good to filter, to understand activity cycles. And the optical is not critical for PRV, with caveat, but it's interesting to get the activity indicators, of course. One key argument in having the infrared is that you have better RV accuracy for active stars in the infrared. There's a lot of work. It's here. It's is it Lac-à-l'Eau? I can't remember. Someone remember the star? Lac-à-l'Eau, no?
It's Lac.
Lac, sorry. There are too many active stars. And sorry, I had a trou de mémoire. Where there's a clear example of a reduction of the jitter. So it's basically you have Spirou and Sophie data over the same time span, and you see a clear reduction of the jitter of these very active stars. It's always more complicated than that. So there's a lot of super interesting work by Pierre Larue in identifying why some lines are more active and less active in terms of contrast. There's a paper coming, and you can read it.
Okay, so Henri Doyon, I'm the colleague of the WB2 work package along with Guillaume Ebra. So we're focused on looking at transiting exoplanet, in particular, these the bulk of the planets found in the solar neighborhood. So we're focused on super-Earths and mini Neptunes, and we really want to have the mass and radius because those are the planets we can actually do atmospheric characterization with JWST. And if you want to, the atmospheric signal that you're measuring is basically inversely proportional with the mean molecular weight, which is basically give you information of the atmosphere composition. But that parameter is also completely degenerate with the bulk density of the planet. So without a mass, we have the radius, of course, but without the mass, we are completely clueless about characterizing these planets. So this is a really important parameter. So ultimately, and when we have mass, radius, abundance measurements, we can measure refractory elements with Spirou very well. And that you can, using internal structure model to constrain the core mass fraction and even the one mass fractions. And of course, with the Recitor McArthur effect, we can actually measure the spin orbit of the planet with respect to the star, which tells something about the architecture of the planetary system. Okay, next slide. Oh, that's me. Okay, yeah. Okay, so what do we expect from Amakihi? So, well, of course, more of the same. We're going to have more targets from, in particular, Ariel, which will open a new parameter space. Well, we'll have lots of giant planets. Ariel will look at a lot of the giant planets, but relatively faint target, which we don't have a mass. And then so Spirou will be very well suited to do this. And also Gaia. Gaia will open a new parameter space for giant planets on relatively long orbits. And that there's only an instrument like CFHT can actually monitor these planets over a long period of time to actually get these masses, and you need stability. And so you need a very good instrument like Spirou to be stable. And so we're talking about several tens of targets we can do very well with Spirou. So again, we want to characterize the mass, the orbit, and again, a very important aspect, you cannot really understand the planet without understanding the star. So stellar activity, it can describe how we can use the D-temp activity indicator to measure the rotation period. And of course, we get that for free every time we take an RV measurement. And of course, we have also circular polarizations, so we can, in the case of bright stars, we can actually detect. And not least, we'll have Espadon with us. So we've seen talks about this. There's a very big difference between optical and ARR, and that will be very, very useful. Okay, and I think that's... one last slide, just to give you the strong synergy we have with JWST. This is TOI 2120. This is a paper in prep by Alexandrine Lheureux. That was observed by Subaru and RD, but then it could not measure the mass. But we have a clear mass measurement, a 5 sigma measurement. On the right, what we show is why we like this planet is because it's on a temperate equilibrium temperature around 400 Kelvin, and at these regimes, the atmosphere becomes clear, and with JWST we see them. So what we see here is K218b, this planet that may have some biosignature, very controversial. But the point is that this one is about the best target we can actually characterize with JWST, and these are simulations with JWST and black. This is what we would expect from 21 to 20, way much better than the current observation that we have. So the goal is to really understand the diversity of these atmospheres. And for now, it's only 2 that's been observed with JWST. So again, this program will actually feed JWST. On this, I will hand it to Nick.
I think the next one is Jean-François.
Okay, thanks for being able to speak. So with WP3, The goal is to study the impact of magnetic fields on star-planet formation, as I mentioned yesterday. And the stars we are focusing on are low-mass PMS stars. Most of them are still surrounded with the planet-forming accretion disk, with which they magnetically interact in the so-called magnetospheric accretion ejection processes. And the goal is to characterize these processes for a range of stellar masses and accretion rates. And we also want to detect and characterize potential close-in massive planets that would be orbiting these PMS stars, and more generally, to characterize the early inner architectures of planetary systems. And the big questions that we want to answer are what types of B fields do low-mass PMS stars host, and how do they evolve with time and with their PMS stage? How do these fields impact accretion ejection processes and star-planet formation more generally? And what is their role, the role of these fields in the formation and survival of close-in planets while they're migrating through the disk? Next slide, please. So what we aim at with Amakihi is similar to what we did before, up to now, with the previous LPs. That is, further constrain magnetospheric accretion models, dynamo models of young stars, planet formation models as well, but do it better than before, thanks to the simultaneous access to optical and infrared domain. And we'll have in particular more lines to constrain, to better constrain the small-scale and large-scale magnetic fields of these stars. We'll have access to complementary proxies to better constrain magnetospheric accretion processes. For instance, we'll have the helium-1 line at 588 nanometer that will tell us about the foot points, the magnetic fields, and also the mass accretion rate at the foot point of accretion funnels. We'll have the helium line at 1083 nanometer that tells us, for instance, about the wind from the star or the wind from the inner disk. And this can only be done by coupling the two instruments. The simultaneous access to optical and infrared and near-infrared domain will also allow us to separate chromatic RV activity from the achromatic planet RV signals, and thereby to more reliably characterize potential close-in planets. And we'll do that by densely monitoring about 50 to 100 PMS stars. Densely monitoring meaning typically 50 visits per star. Use spectropolarimetry, of course, Stokes IV always, and possibly Stokes Q for the brighter stars to characterize their large-scale and small-scale magnetic fields. We'll also monitor activity and accretion ejection processes on short time scales, but also on longer time scales for the activity and possibly the activity linked to the planet. And we'll use synergy with VLT gravity, for instance, to better localize the accretion funnels, to further constrain models of magnetospheric accretion, and possibly with JWST as well to characterize close-in planet atmospheres. And Nick will talk about that just after me. So the last slide, please. That's a typical example of what we could do with Amakihi, and in particular with vision. We were lucky enough to do something close on the classical Titori star, so Ci tau, not with simultaneous data, since we didn't have vision at the time, of course, but with contemporaneous espadon and Spiro data. So this is not enough to really study magnetospheric accretion processes from both domains, as these processes vary on very short time scale. We really need simultaneous data for this, but we were able to study the large-scale magnetic field of Ci tau much more accurately than before, much more reliably than before. And this is, to our knowledge, the most reliable map ever obtained for a PMS star. So we used all these lines that are mentioned on the slides here to diagnose a 1.1 kilogas dipole field tilted at 15 degrees with respect to the rotation axis. So with that, we'll be able to study, again, Titori stars and all these PMS stars in much more detail. So up to you, Nick.
Okay, now it's my turn. So I'm going to talk about work package 4, which is exoplanet atmospheres. And I'm not going to go through everything here. I'm just going to give you a few of the highlights. One is the K-band that Spiro offers, which means You can do carbon monoxide, which is critical because most of the other molecules on hot planets eventually get dissociated. So if you're looking at the very hottest planets, even things like water vapor cease to exist. So that's critical, and Spirou is nearly unique in having access to that at high resolution. Another thing that's a critical difference over, let's say, the James Webb Space Telescope is that we're doing this at high resolution, which means we can see Doppler shifts of lines. So we can actually directly probe winds in exoplanet atmospheres, which we can only try and infer sort of indirectly with things like James Webb. And then some of the other highlights, well, you get a bunch of molecules. You also get things like helium. You get atomic lines at optical wavelengths. And the ability to do simultaneous optical and near infrared is critical because we now know that some of the helium lines, which are probing basically atmospheric loss from exoplanets, they vary in time. And the question is, are they varying in time because the actual atmospheric loss is time variable due to space weather, or are they varying in time because of the kind of radiative transfer of exciting this helium metastable state? So these are the kinds of questions that we could uniquely answer with this combination of Espérance and Spirou. So what you could expect from Amakihi, the best 3D constraints, really 4D. Like we're looking at planets in multiple dimensions because of the radiative, because of the radial velocity component. We can actually see the parts of the atmosphere that are moving towards us, moving away from us. We can see emission from lines that are only present in certain places in the atmosphere. And we can see how things change in time by basically hitting the same planets, the best signal to noise planets, over and over to actually see meteorology in their atmospheres. And again, things like space weather, when we look at time variable helium probing atmospheric loss. And my diagram is basically just a transit spectrum showing that, you get these lovely optical lines here, which are mostly probing just atoms. And then you get all of the rich forests of lines of the molecules. And those different domains are probing different pressures in the atmosphere, which means, again, we're really mapping these planets as, we're like way beyond the spherical cow. Like we're now really mapping them in multiple dimensions and actually seeing things shift. And like, how does the wind velocity, how does the jet stream on one of these planets change as a function of pressure as you move down into the atmosphere? So that's it for me.
Thank you. So, of course, a community survey involving spectral parameters has to include a thread on stellar magnetism. The instrumental suite that is already available at CFHT is unique worldwide, and it will be even more unique with WNAO-KRO. Okay, and actually, stellar magnetic fields are critical ingredients in many aspects of stellar physics, and we do detect magnetic fields from M dwarfs to O stars, and from the early stages of stellar evolution to the ultimate phases of stellar evolution. So what we get specifically in spectropolarimetry, that's the magnetic field at the surface of the star, which is a boundary condition that help us better understand the internal physics of the star, but also can be used to develop models of the closed environment of the star and better understand, the space weather around the planets that will be detected as part of the community survey, for instance. So why is WNAO-KRO opening completely new perspectives for us? Well, the larger the spectral domain, the higher the magnetic sensitivity you get. And so with WNAO-KRO, we increase a lot our capacity to make accurate magnetic field measurements, meaning that we'll be able to explore stellar classes that host very weak magnetic fields, out of which, as of today, or stars that are a bit too faint to be also observed today. And also, we will combine, thanks to this huge spectral coverage, we'll combine these polarimetric magnetic field measurements with a diversity of spectroscopic proxies of magnetism and stellar activity. So, and of course, we will be able also to make long-term monitoring of magnetism, which is critical to us because a lot of what happens with magnetism is variable. That there is some variability and long-term variability to be explored, of course. And it is especially difficult right now for Espadons, for instance, because the low availability of Espadons on the telescope makes people refrain to proposing some proposals, because we know in advance that it is not compatible with the low availability of Espadons at CFHT. We will take advantage of observations from more packages 1, 2, and 3, because they will provide us with spectropolarimetric content for free, okay? But since not everything is related to M dwarfs or young stars, we will also have specific focus science questions that will be dedicated to other classes of stars, I mean massive stars, so type stars, for instance. And I will not show you a highlight like the other threads, because you will see that the next 2 talks will in fact highlight 2 possible science cases addressing the magnetism for Amakihi. Okay, and next one I think is Vanessa. If you are online, Vanessa, that's
I am.
I will have the slides.
Yeah. If you can move the slides for me. Thanks. So galactic archaeology, as you've heard from several previous talks, I believe, is the art of using chemical composition and dynamics together to understand the details of galaxy formation, and in particular on how our Milky Way has formed and evolved. In that context, very old and or extremely metal poor stars in the Milky Way are direct fossils of how the galaxy assembled and what the universe looked like at the earliest epochs of star formation. And they have, therefore, a very important role to hold in that context. From these very metal poor and old stars, we want to constrain, in particular, what the population 3 stars, those that were formed from pristine gas at the very beginning of the universe, have left in terms of chemical imprints on the next generations of stars, and how we can constrain these population 3 stars from these imprints. We also want to understand what is the part of the Milky Way that was formed in situ in the primitive Milky Way versus what was accreted. And you see on the top plot, on the right-hand side of the plot, what Gaia gives us, which is basically the exquisite dynamics of old and metal poor stars, and from which you can actually see the circles here are different substructures that were identified dynamically. And to really understand what kind of systems actually assemble to make the Milky Way, you need to understand in details their chemistry, and this is what is done on the left part of the plot, where this is a follow-up of some very metal poor stars in the south from Uvis and in the north from Espadon. This is a paper by Philippe Ground in preparation. The other things that Gaia does, and that is very important to galactic archaeology in a different way, is that it identifies a wealth of different binary stars. And what you see here on the bottom left is actually the most massive known black hole in the Milky Way, stellar mass black hole in the Milky Way, which is orbited by a low mass metal poor star. And these systems are extraordinarily interesting because they hold some information about how binary systems evolve once such black hole or neutron star component is included. And in particular, we really don't know at this point whether the black hole binaries are the result of isolated binary evolution, or whether they are only produced by dynamical interactions in clusters. And this has a strong link with actually the gravitational wave detections of binary black holes and neutron star mergers, which may be the source of our process elements in the Milky Way. So next slides, please. So what we're looking for with Amakihi is to complement these beautiful data that are given by Gaia in particular for extremely metal poor and old stars. And to give from Amakihi and from the large wavelength range that the combined Spirou and Espadon gives us, the measurement of many elements from the very blue for neutron capture elements to the near infrared for CNO elements, to constrain the chemical part of this whole Milky Way assembly picture. And at the same time, we also want to follow up with very accurate radio velocity measurements, the binaries that have been detected or will be detected by Gaia in the upcoming DR4 and DR5. And I think I will stop here. You see just the equivalent, the radio velocity curve for this black hole detected by Gaia here on the right, and some detections with Espadon of neutron capture elements for a bunch of extremely metropolar stars.
So rapidly mentioned already, but so work packages overlap with 1 minute, but we're wrapping up. Work packages overlap, as I said earlier, with space missions. I guess that's the last slide. We mentioned those already. So here's a cluster of words, and we will welcome your questions. I guess we want to leave some time for questions. You at least have one question per work package, I hope.
On passe le micro pour... ouais. Non, mais faites les autres aussi. Si.
This is Damien Swami from the Observatoire de Paris. I have a work back. Nice talk to all of you. Amazing science. I look forward to that. So I have a question, possibly comment / idea to work package 4 about exoplanets atmospheres. So what resolution are you expecting? And then I have another follow-up on that.
Like the spectral resolution?
That's correct.
I mean, it'd be the current spectral resolution. What is it, like 78,000?
Yeah. 70-ish%, yeah. 70-ish resolution that you're expecting. Okay. And the other thing, well, you mentioned the connection with space missions like Ariel, etc. I'm coming back to my Neptune atmosphere, actually Uranus. We got contacted by the Ariel consortium, and they have recognized the importance of the Uranus atmosphere studies, and they included that in the additional science case of Ariel. Maybe we could speak about work package 4B, where we're talking about atmospheres of Uranus, Neptune, and giant planets in our solar system.
So like solar system observations. So I know, Etienne, you've observed Venus with yeah.
Let's look at making Venus date. I was thinking with observations of Venus, where you see the thermal from the basically in K-band. You see thermal emission of Venus. I don't know what's the status of the data. Well, it's reduced, and we were happy with the processing part, and it's in Thomas' hands. So I don't know.
I just want to add that, let's suppose that these Uranus targets are included in Ariel and they are observed. Again, as I said, in all likelihood, there won't be any mass for these planets. We'll need a mass, and this is where work package number 2 becomes really important.
Okay.
Yeah.
So it depends if you want variability of solar system objects or...
We do want that.
Okay, but then there's a time aspect to it. Otherwise, it could be a PI program.
We do want the variability.
Okay.
Yeah. And there are a few events that, I have all list of events until 2050, as I was mentioning earlier. So until 2033, I can send you the list by tonight.
It could be interesting to consider.
Thank you very much for very interesting presentation. So, Victor Halak in Stade Moncton. I'm most interested in this, like all the groups which we will be working there, and like you doing spectropolarimetry. But first of all, when it will start that survey? Second, has it already started, or you just proposing?
Well, it's a proposed community survey. It's on the horizon of the community survey, so the end 26, something like that. 7, 8.
So you just proposing, so there are some other ideas that can be incorporated to this survey, because I know the CFHT has asked for the ideas. Okay, people, please provide ideas.
It's the idea of constructing a coherent programs, but yeah.
Okay.
Of course, yes.
Great, thank you. So how is it going to work? Because we have like PI programs, we have some programs in C-band,
that already testing those ideas. So how you going to select the targets for this survey? Could you please elaborate a little bit more about that?
Well, we're here to advertise this community project, and this is for you, to react. And, if you have ideas to bring forward, please go for it. It's for everybody to bring you ideas to add to what we've already described here. It's not, in concrete, this thing now.
If I may comment, what should be in everybody's mind, as my suggestion in discussion with Claire, is what's the added benefit of having 5 years worth of data versus if it's your pet object, you want 10 visits, there are PI programs, and there will be PI programs. So we really want to convince ourselves that, let's say, the 5 years plus the commitment to it. And one example that just comes to mind, the Gaia trends, you need 5 years of commitment to get an orbit that's, they say, 8 years with Gaia. It's not true that you will get it with 2 snapshots. It's not true that you can get it with program. And the tech will tell you, come on, it's 2 years that we're giving you time, and you're not getting it. You're not publishing. So that's an example of something that needs a commitment. It's just one that comes to mind, but yeah.
No, I'm sorry. It's again me, Victor Halleck. Why the question like this is because, for example, if you take Ariel, they already pre-selected the target that's going to be observed. Nick already knows that. So we already selected the targets that are most favorable for observation with CFHT, that we can get the largest signal-to-noise ratio. But again, it's like 20 targets. You have to select from them like at least 10% that can be favorable for this community survey. Another question, again, related to this, when the just test data came, give it 1 year, we just detected new raw AP stars that needed follow-up. 2026, we'll have plateau, and I guess we have, again, a lot of interesting targets that are going to be discovered, and we need to drop in with some extra target to be followed up spectropolarimetric.
Okay, so I'll answer the aerial thing and pass it back to Etienne or someone else for Plateau. So for aerial, we have a superset of the mission candidate sample. We do not know the actual mission reference sample. So we have not yet decided which 1,000 planets we will observe. We have 3,000 or so planets that are planet candidates in half the cases that seem very promising. So this is one of the huge tasks that I think this program could contribute to, is just getting RV masses for a bunch of these test planet candidates to make sure that they are actually good vetted planets with known masses so that we can do atmospheric characterization with aerial. And then related to that, for atmospheric characterization, there's things we can do from here, from the ground, for example, helium detection that is impossible for aerial. And so that would be very complementary. Even if we could do that for like a few dozen hot Jupiters or small Neptunes or something, that would be super complementary and useful for aerial. And then for Plateau, who wants to talk?
Well, I just want to make a general comment that in this kind of survey where we don't have the targets yet identified, as Nick mentioned, so we need flexibility into the actual program. We can describe in general what the science we're going to do. But so we have to be flexible. So there's an incredible target coming in, and so we have to be able to just slot it in. We do that on a different survey on NIRPs, for example. We have to declare targets that are frozen, but some of them just goes out and some goes in. So there's some flexibility in our allocation. So how we'll be able to do that?
I can reply maybe for Plato, if it can help. For Plato, there are 2 kinds of targets. There are the solar type stars that are being selected by the consortium. And for all the other types of star, there will be a call for geo proposals in the spring next year, so about 6 to 9 months before launch. And then it is up to us, the community, to propose the targets that we would like to observe. So we are not waiting for Plato to tell us which targets will be observed. We have to tell Plato which target it should observe within the field of view of Plato. So the field of view for the first 2 years is already selected. It is in the southern hemisphere, and we can propose any target in this field that is of interest.
One question. Do you have an idea of the fraction of dark time you would request?
All of it, obviously. Why do you ask? It's a hard question. It's a hard question, but okay. I won't answer directly because it's not easy. But it's above my pay grade. But in Spirou targets, we're really struggling around 30 days, 28 days for obvious reasons. There are gaps, and there are planets at 28 days around all M dwarfs, and it's problematic. Do we need a half of the dark time? Do we need to sneak in half of it, up to half the dark time? I don't know. But and it should be simulated properly. But we suggest a significant, and whatever is significant, maybe a half. I don't know. Jean-François and Claire may send emails disagreeing, but we may have issues with that.
So even for atmospheric characterization, it's a real bitch to schedule if you want to do multiple orbital phases of a hot Jupiter. We've discovered to our chagrin that even if you pick a few targets and say we're just going to hammer these all semester long, you actually struggle to construct like phase resolved observations because you're on sky only half the time, and then combined with the fact that the sun's up half the time, and you get too many factors of a half. Basically.
Okay, so thank you very much for this breakdown. And thank you for the team to have built already this kind of community survey, and it will grow before the final observation.